Hello, in this video we're going to talk about how to linearize your data. If you take data and it looks curvy and you think it is not a linear or proportional relationship, then you will need to linearize because we so desperately want to put a straight line on our data so that we can do some min-max lines, some uncertainty, and some slope analysis. So there are some tricks we can do to take our original graph and do some math so that we get a graph that's straight so that we can do a regular old slope analysis on this. So that's what we'll go through today. Here's some example data. We're going to look at this through the lens of an example. Please keep in mind the process will not be exactly the same every single time. The type of linearization we do here may not be the type of linearization you need to do on your data. So this is an example. This is not a do exactly this every time type of thing. So try and focus on why we're doing it, and then you'll have to think about your data and apply it to your data. But here we have some data. This is probably a naughty student who has only taken 3 levels, but for the purpose of this example, that's totally fine because we get a graph that looks like this. You could almost imagine that maybe we could try and force a straight line to fit through this data, but it definitely doesn't seem like that's the best fit, especially because it would be way off of the origin. And most things in physics we expect to, if we're looking at displacement in time, say how far something has fallen at different times after release. We sure know from running the experiment and thinking about what our data means that our trend line should, in a perfect world, go through 0. So if we think about that, then this seems like it's going to be probably pretty curvy. So we want to think about what kind of curve would be appropriate for our data. And what we're going to choose is a power fit. We're going to use a power fit in LagerPro. Power is the only thing you should ever put on your graph other than linear, unless you're like 900% sure that it's definitely something else because you know a lot of physics. You should never, ever, ever pick any kind of polynomial. You should never pick quadratic, cubic, quintic. They'll all fit perfectly, but it doesn't mean anything. So power or linear are really your only 2 options. So if it's curved, you pick power. We can look at this, and this is what LagerPro is telling me. It's telling me usually y equals a x to the b. Since we call this displacement in time, my y-axis is s, my x-axis is t. Of course, that'll be different for every experiment. The important number is the b, though, because that's the power. This is saying LagerPro will tell me what the best power is for my data, what kind of power I'm dealing with. So this is what LagerPro is telling me, that my displacement is 2.86 times t to the 2.07 power. This is the important part. LagerPro is telling me that the best power for my relationship is 2.07. So now I have to kind of think through what might be a reasonable, actual physical relationship that I think exists in a physics sense. Because you could look through the whole data booklet, I promise you will not find a 2.07 power in nature. But of course, because of error, uncertainty, all that, I expect that this isn't exactly what it kind of, quote, should be. So I need to make a guess. And I would guess that this is supposed to be some kind of squared relationship, some kind of second power relationship. So k is just a variable to represent the coefficient out front. It's not nearly as important as the power. So I'm guessing second power. That sure seems like the best bet for this relationship. Please notice this is not a quadratic. You will never really see a quadratic. It's not kt squared plus bt plus c. It's just kt squared, right? It's a power relationship. There is a difference. So please, please, please don't use quadratic. All right, so in other words, I think that my data is showing me that the displacement is proportional to t squared. This is the important part. I think my displacement depends on the time squared. That's what this is all telling me. So if I think 2 things are proportional, if I graph those 2 things, I should get a straight line. So in other words, if I graph s and I graph t squared, I should get a straight line. That's what I'm going to try. Here's another way we can look at it that might be helpful to make it a little less weird. If I think about this equation, I just want to treat t squared all as one thing. So let's just call it z. Let's just call it some other variable so we can look at it in a cleaner way. S would be k times z. This is a directly proportional relationship. This is like a y equals kx kind of thing. So if I'm looking at this, if I plotted S versus Z, I would get a straight line that goes through the origin, which means I would plot S versus T squared. Again, I think those two things are proportional. So if I plot S versus T squared, I should get a straight line and I should be able to do some stuff. And this will allow me to show in my report that the relationship between the variables is that S depends on T squared. This is how we're going to do it. That means I need to literally take the numbers for time and square them. Let's see, before it was like 1, 2, 3. Obviously, your numbers will probably not be so easy, but just for the sake of example, we literally just square those numbers because I think time squared is what really matters. I think time squared is proportional to displacement, so we'll try that. If I make a new column in Excel, or I can even have Logger Pro do this for me, and I use these values. I'm going to plot the average displacement versus time squared, so I actually calculate the times squared. Notice we got to change the title of the table and some other things too. The units become second squared. The uncertainties would all change. I'd have to propagate error for my time squared. But it turns out when I plot it like this now, I can see they make a nice straight line. And of course, this is exciting because now I can do minimum maximum lines. And now I can talk about the relationship between displacement and T squared. Notice we're changing the title, we're changing the axes labels, my units change. It looks like I get some kind of acceleration in this specific example. So here are the steps that you can take. If you have curvy data at a power fit, you will show that original graph. So you will present a graph in your report that looks like this with the power fit on it. There's no minimum maximum lines because it's not a straight line. But you do want to show this because you'll reference the power to sort of justify how you linearize. So you start with that. Please, please, please remember, linear or power are the only things you're ever going to use. Decide what exponent makes sense to you, what's a nearby mathy exponent that you think makes sense that would show up in a physics equation. In Logger Pro, you can have it do this for you, and it becomes really easy because it'll let you toggle. So we're usually going to do x to the b. We saw time looked like it was raised to the second power, so we calculated t squared. If you go to data, new calculated column in Logger Pro, it'll let you write a formula, and you can write a formula that takes your times and squares them. It'll make a new column for you, and you can toggle back and forth. It makes things really easy. You'll need a new results table. You need to propagate error. And then we're going to graph y versus x to the b. So in this example, we graph displacement versus t squared. This is our linearized graph, and that's the second graph we're going to present. Next, you add a linear fit. If a straight line goes through your error bars, you have chosen a good linearization. You are justified. Make sure you're considering what happens when you change your variable. Uncertainty will change, units will change, all your labels and titles will change. Just like in the last one, we had t squared, so that had to show up everywhere. And then you're going to do slope analysis on this new linearized graph because now we have a straight line. And the whole point of this is that I can get a straight line, do slope analysis, talk about the slope, find an uncertainty, all that stuff. Keep in mind when you're doing this, the units have changed. So when I'm doing my slope analysis for the example here, I'd have to be thinking about meters per second squared. So this is the order that this should appear in your report. You show your original results table and graph. This would be the one with the power fit on it. Then you show the linearized results table. That would be the one I had with t squared. Show your results graph that's been linearized, and then do slope analysis on that. So if you're linearizing, you'll have two results tables and two graphs. All right, so use this video to help you out as you go through. Remember, you're going to have to try and think through and make sense of your data. It will not always be the same as this, but this process should help you out. All right, have fun.